Welcome to lesson 3.3. So on this lesson, we're going to look more with change, and we're going to translate some problems in a few different contexts into mathematical representations. We're going to identify when a model is linear and interpret the slope and the y-intercept. And we're going to use functional models to make predictions. The main idea here are playing with linear models. Slope is a rate of change, and that rate of change has units that are important. And then you can read through the other fine points. So let's do some math. So in lesson 3.2, we looked at blood alcohol content and considered the example of the 120-pound male that had 3 drinks. So his initial blood alcohol content is this calculation here. We ended up with 0.104. And the constant change we had going on was that negative 0.015. And what we found when we played with the table with these values is that for every hour that went by, his blood alcohol content dropped by 0.015%. So again, the linear model formula looks like y equals mx plus b. M is the slope. Slope is a rate of change. And a rate of change is a fraction where you have two things changing. So in this case, our change in y, that was the drop in blood alcohol content as a percentage, and the change in x was the increase in each additional hour. So that's the idea of linear change. And so again, we, in the previous lesson, graphed the situation and we found that this person's blood alcohol dropped in kind of a straight line pattern according to this formula. So let's look at a few other examples of linear change. Fahrenheit versus Celsius is a pretty good one. 0 degrees Celsius is the same as 32 degrees Fahrenheit. That's when water freezes at sea level, and then 100 degrees Celsius is 212 degrees Fahrenheit. That's when water boils at sea level. And if you're curious about what happens when you're above or below sea level, then take a physics class. It's awesome stuff. Again, slope is our rise over our run. So if we were to say graph Fahrenheit versus Celsius, and we had Celsius there and Fahrenheit here. When Celsius is 0, Fahrenheit would be about 32, and when Celsius is 100, that's 30, that would be like 60 there, and then 90, 120, 160, I missed something, 180, 212, somewhere up here. So this would have a line, ooh, that looks something like that. Again, the change in y means you have to subtract 2 y values. Change in x means you subtract 2 x values. And here I would consider this second line to be my second point and the first line to be my first point. So my y2 would be the 212, my y1 would be the 32. And the order of those doesn't matter too much. What does matter, though, is you line up the points vertically. So the 212 and the 100 have to line up. The 32 and the 0 have to line up. 212 minus 32 is 180. 100 minus 0 is 100. If you reduce that, you get 9/5 as a fraction, or 1.8. And we can look at the slope either way. As far as the 1.8 goes, slope is a fraction, so I would rewrite that as 1.8 over 1. Remember, 1.8 came from the Fahrenheit, so that would be degrees Fahrenheit change, and the 1 or 5 or 100 came from the Celsius, so that's degrees Celsius. Putting that together into an equation, I've calculated my slope is 1.8 simplified. My x is really a Celsius temperature, my y is a Fahrenheit, and we start at, when Celsius is 0, Fahrenheit's 32. So that's my starting point for Fahrenheit. interpretation of this slope would be that for each increase in temperature of 1 degree Celsius, there would be a rise, positive, of 1.8 degrees Fahrenheit. So that's an interpretation of this particular slope. Another example. I like to ride my bike, and I live in a pretty middle of nowhere place that's relatively flat. And so let's say my home is over here, and I drive my car and park over here and pull out my bicycle, and then I'm going to go for a bike ride that way. And then I started 10 miles from home. Now once I jump on my bicycle and start biking, I can average about 15 miles per hour. So my slope, my rate of change here, is going to be a positive 15 miles for every additional hour that I go. And so it's important when you're trying to interpret a slope that you think about the fraction, and you have to consider what's the independent variable and the dependent variable. And so back here, I had that written down. The y is typically dependent, x is independent. Sometimes that's arbitrary, sometimes it's not. In this case with the blood alcohol, time is independent. It keeps going, there's nothing we can do about it, and pretty much everything else depends on it from our perception. So in this case, I have my miles per hour. The hours just go by, so that's going to be my x, my independent variable. And then the y is going to be my miles, and that depends on the time that I check on what's going on. My starting point is that 10 miles from home. So as far as y equals mx plus b goes, y is changing, right? That's my distance. That depends on my time I look, x, and 15 is my slope. Plus, I started 10 miles from home. So I can make a quick table of this situation. I'm starting out 10 miles from home, and then an hour goes by, right? And I'm just kind of cruising down the road. An additional 15 miles happens, so I should be 25 miles down the road there. The second hour goes by, another 15 miles happens, so that gives me 30 or 40 miles from my house over here, given that I started there and I'm just going in that direction, right? So in a table, if your x values increase by the same amount each time, and your y values increase by some amount, in this case I'm going up 15 each time, if they both increase steadily, 1, 1, 15, 15, this is what we call a linear pattern. And that's related to that equation right there. Interpretation of the slope right here would be that for each additional hour that I ride, I cover 15 more miles. And so I want to get across a couple of things. Again, slope is a rate of change, so I have to have one thing implies another, right? Every 1 hour, 15 miles is covered, and it's also additional, okay, and more, because they're both changing. Let's look at another example. When it's too cold to bike and there's snow around, I like to ski downhill, and Anthony Lakes, Oregon is a beautiful place. So cool thing about Anthony Lakes is the ski lodge is about 7,100, and the ski lift takes you up to about 8,000 feet, so I get this 900-foot drop I get to ski on. I'm a relatively slow skier, so let's say I ski downhill at about 20 feet per second. So if I wanted to take a look at my altitude when skiing over time, and I measure the altitude in feet and the time in seconds, because that was the speed I was given, then I can come up with a linear equation for that, y equals mx plus b. So my altitude y is going to depend on a couple of things. Again, my rate of skiing. So let's suppose that it's just a constant slope and I just stick with it, and that I started at 8,000 feet, right, top of the ski lift. So that means I'm going to drop 20 feet per second for every x second that goes by, starting at 8,000 feet. Okay, so that would be my linear equation to match this situation. So my starting point, right, I'm starting at 8,000 feet when we start counting. And my slope, as far as an interpretation, would be for each additional second that goes by, my altitude drops by 20 feet. Altitude, there we go. So again, the rate of change, I have to take into account both the dependent variable and the independent variable. And usually we start with the denominator, the independent variable, and how that changes the dependent variable. And then we also want to get into consideration the change. So there's a change each additional second, and then my height's going to drop. All right, another example. This one's kind of lame, but we're going to take a look at just the simple expression here, y equals, or equation, negative 2/3 x plus 3. So my slope, m, is negative 2/3, which, by the way, could also be viewed as 2/-3, because a positive over a negative is a negative, and a negative over a positive is still negative. So this slope has a couple of different interpretations we'll see. And my starting point would be the point 0 for x, 3 for y, because of that 3 right there. So let's throw in a line for the y-axis. How about we put that right about here-ish? And a line for the x-axis, maybe right there. And make a few marks on there. So let's say this is 1, 2, 3, 4. 1, 2, 3, 4. And a couple of others. Negative 2 there. And negative 2 over here somewhere. So let's see, my starting point is 0 for x, 3 for y. So that means don't go left or right, but go up to 3 there. So let's graph that in blue. So there's my starting point. And then this says to change in y means drop 2, and the run means go right 3. So 1, 2, 3. Should put me about right there. And I can keep doing that. I can drop 2 again, and then run 1, 2, 3, should put me there. Now if I use the other interpretation here, then I'm going to go up 2 and left 3. So 1, 2 over 1, 2, 3 should put me about right there. So let's see, where would I be there? That would be negative 3 for x and 5 for y. 6 for x, negative 1 for y. So let's just check that out in a table here. So according to this, I should have the following points. I go with this line right here. So let's start over with the leftmost one. -3, 5 should be on this line. 0, 3 should be on this line. 3, 1. And what was that? 6, -1. And let's pick this one as a test case. So if I plug in x equals 6, let's see what happens. Hopefully I get -1. So I'm kind of checking my work. So 3 goes into 6 twice. And 2 times -2 is -4. -4 plus that 3 there gives me a -1, which is just what I hoped. So the slope did give me a series of points that line up, and they seem to be on the line that matches my equation. So I'm going to draw a line through here to the best of my ability with this tool. So that roughly should be my line. And I'm just going to throw some arrows on it to indicate it heads that way forever and this way forever. All right, last example. Let's look at population change. So I grew up on the East Coast in a little state called Rhode Island. According to the U.S. Census Bureau, in the year 2000, the population was 1,048,319, and in 2010, they counted 1,052,567 people. The difference in those two populations is an increase of 4,248 people per year, which is about a 0.4% rise in population over that 10-year span. So I'm going to take this into a spreadsheet and play around with it and do a prediction. All right, so I have that typed in here. And oops, I lost a number. Was that 1,050? Nope. Let's see, I lost it. 52,567. All right. 52,567. And if your number isn't automatically with commas there, you can use the number format and then just drop the decimals if you don't need them. Absolute change is just the difference. So equals the newer population minus the previous population. So there's my increase of 4,248. Now that's not the slope, that's just the rise. I have to take into account the run of 10 years. So to get the slope, I take my rise and divide by 10. So that gives me an increase of 424.8 people per year. Now we can't have 0.8 people, so we would, probably round that to one decimal point, like 425 people per year. What I want to do is take that information and make a table, and I'm going to go years after 2000. So that would be a 0, 1, 2, 3, and I want to get up to 10. So I can auto-fill that down. And actually, I want to keep going. I want to go to 2020. There we go. And the formula for this, let's do a little calculation. So I want to come up with something like y equals mx plus b. And my m, my slope, is going to be my change in population. That's going to be my y over change in years. And so I have a change in population of 4,248 over 10 years, which gave me that 424.8 people per year. I'm choosing my x to be not the year, because then x equals 0 would be that line between AD and BC, which is a little weird because Rhode Island didn't exist then. So I'm going to simplify that to be years after 2000. y is just going to be the population in that year. And so my formula then should be the slope of 424.8 times the years after 2000, plus the initial population in 2000 of 1,048,319 people. And so I'm just going to apply that to my spreadsheet, and my spreadsheet will just pick the right year in the year column. So for population here, I can just type equals to do a calculation. And I want to take my slope, 424.8, and multiply that by the current year, and add on the initial population of 1,048,319. Okay, so I get my initial number back because I know time has gone by, and then if I drag that down to the 10th year, I should get that population from 2010. Perfect, that worked well. And if I keep filling that down to 2020, I can make a prediction what's going to happen in next year. So I'm predicting, according to the census data, that if the population continues to rise at the same absolute rate in terms of linear slope, that the population next year in Rhode Island should be about 1,056,815 people. So let's see if there's any other predictions online to compare that to. So I'm just going to search for Rhode Island, and up pops Wikipedia, one of my favorite sites ever. And Wikipedia will likely tell me some information in this sidebar here. And here we go. Wikipedia claims that the population total in 2018 was estimated to be 1,057,315. So let's grab that and stick it in the spreadsheet for comparison. Control C to copy. Oops, wrong page. There we go. And 2018, Control V to paste. So notice it's a little bit different. So Wikipedia got its information probably from the Census Bureau, and the Census Bureau does intermediate guesses at populations in different regions. They're not official, and that's my guess where Wikipedia got that. And so notice that's a little higher than what my linear change predicts. So that could be they're using the percent change that was given. Let's see, somewhere I have, where did that sucker go? Ah, yes, in the Share Your Work, I have a link to a Census Bureau document. And on the second page, they have a table. So the Census Bureau predicts for Rhode Island, for example, that there's going to be a 0.4% change. So they got that by taking the absolute change, the 4,000 people, and dividing by the 2,000 population. And that comes out to be about 0.4%. And we'll take a look at that percent change idea in a later module. So let's see, is there anything else we need to look at here? I think that's about it for now. So take care, do good math, and I'll see you in the near future online.